Hi, I'm Naty Hoffman, Principal Engineer and Architect at Lucasfilm's Advanced Development Group. In this talk, I'll try to shed some new light on a familiar topic, the Fresnel term. I'll start with an overview of its history. Fresnel's equations were initially published in 1823. They hold for light reflecting from a perfectly planar mirror surface. The equations depend on the angle of incidence, theta, and are parameterized by eta and kappa, which together comprise the complex index of refraction, or IOR. Eta and kappa values may vary for different wavelengths over the visible spectrum, especially for colored metals such as copper shown here. For dielectrics or nonmetals, kappa is 0, which simplifies the equations considerably. Microfacet theory, introduced by Torrance and Sparrow in 1967, expanded the use of the Fresnel equations to more general surfaces, by treating them as statistical assemblies of perfect mirrors. However, there are surfaces that cannot be modeled as a simple interface between an exterior and a uniform interior. The Fresnel equations do not apply in such cases. For example, loosely packed fine dust, with individual grains smaller than a visible light wavelength. In this case, the transition from air to dense dust is a gradual one, passing through a continuous variation of refractive index values. Other examples include surfaces exhibiting thin film interference, where the light interacts with multiple layers, or diffractive surfaces, which have repeating structure at a scale smaller than a light wavelength. Blin's 1977 paper was the first notable use of Fresnel in computer graphics. He proposed a microfacet BRDF which required multiple angles. Theta h is the incidence angle of the individual microfacets, which use the half vector. And theta I and theta O are the incident and outgoing angles with respect to the macroscopic surface normal. The paper only mentioned Fresnel briefly and somewhat inaccurately, applying the dielectric form to both dielectrics and metals. Like Blin's paper, the 1981 paper by Cook and Torrance was based on the Torrance-Sparrow microfacet model. The Cook-Torrance paper also contained an in-depth discussion of spectral Fresnel computations and their relation to final RGB pixel values. This discussion had three main parts. A full procedure with spectral computation of reflected light spectral power distribution, or SPD, and then conversion to RGB pixel color. An approximation of the above based on color interpolation. And finally, a procedure for approximating spectral eta and kappa from normal instance reflectance. It turns out that the third procedure yields gross errors and should not be used. Further details on this are available in the course notes. Fortunately, that part is not key to the paper, so we will focus on the other two parts. In the full procedure, the Fresnel equations are evaluated for a given instance angle theta, and for a dense spectral sampling of IOR data. This example shows measured data for copper. This results in a spectral reflectance curve. The spectral reflectance for the current angle is then multiplied by the SPD of the incoming light to yield the SPD of the reflected light. The reflected SPD is converted to perceptual RGB values in the standard way: multiplication by color matching functions, integration of the results, and matrix multiplication, resulting in the final RGB display value. For now, we will visualize the results for the 0 to 90 degree range of incidence angles in two ways: as plots for the values of the RGB channels, and as a color strip. Since most of the variation appears at glancing angles, we'll also zoom in on that part of the angle range. As expected, the characteristic copper color of the material appears at an angle of 0 degrees. The value at this angle, f0, will appear a lot during this talk. The same color extends almost unchanged over most of the range. For this reason, f0 is a key parameter for describing the surface appearance. Finally, there is a rapid transition to white close to 90 degrees. That was the full procedure. We will now describe the approximation. The Fresnel equations are used with a single representative IOR value, resulting in a scalar function we will call f prime. The value of f prime is used to interpolate between f0 and white. We'll present a version of the approximation that is slightly modified from Cook and Torrance's original version. It produces much better results than the original, while preserving its spirit. More details in the course notes. We use a complex IOR value sampled at a single representative wavelength. Note that the f prime values are all scalar, and the f theta and f0 values are wavelength dependent, most often RGB. This is a reasonably good approximation, as we will see when comparing its results to the ground truth results. When flipping between them, we see that the approximate curves have a slight corner to them, but are otherwise very close to ground truth. The color strips, on the other hand, are indistinguishable. So how should we decide what procedure to use? Cook and Torrance saw their approximation as much more than a mere optimization. They stated that it must always be used if the renderer does not have accurate spectral data. But this condition almost always applies to production rendering, which typically does not use accurate spectral data. This is especially true for RGB renderers. But even spectral production renderers, such as Manuka from Weta Digital, use spectra that are upsampled from RGB values. It's also interesting to note which option Cook and Torrance did not include. In particular, running the Fresnel equations on RGB values directly. This was not an oversight. This option was not mentioned for very good reasons. To understand why, let's discuss the nature of RGB rendering. It's a common misconception to think of RGB values as a less accurate version of spectral values. However, they're actually quite different. RGB color spaces are only meaningful for expressing perceptual quantities, but physical rendering math, such as the Fresnel equations, work on physical quantities, which need to be expressed spectrally. The only physical rendering quantity that is also a perceptual one is radiance, which is directly processed by the human visual system and thus can be meaningfully expressed as an RGB color. RGB is also used for reflectance colors, which are defined indirectly as reflected radiance from the white reference illuminant. In a sense, reflectance values are perceptual adjacent. In contrast, quantities like eta and kappa have no perceptual analog. The relationship to final rendered colors, perceptual stimuli, is very indirect and highly nonlinear. Technically, RGB rendering is a category error, performing physical math on perceptual quantities. In practice, it works well, if we are careful. Simple linear operations on RGB colors are fine, but complex nonlinear operations will cause problems. As we saw earlier, the Cook-Torrance Fresnel approximation divides pretty cleanly into a nonlinear scalar section and a linear RGB section. The nonlinear scalar term is only used to interpolate between two colors. However, RGB math with the full Fresnel equations involves nonlinear operations on perceptual RGB quantities. This can introduce various issues, as we will see later. To further illustrate the problem, recall the full procedure outlined earlier. To compute an RGB color correctly for a given angle, you have to go through this rigmarole, apply Fresnel to spectral data, and then carefully convert the result to perceptual colors. But if we were to apply the Fresnel equations directly to RGB values, it would look like this. RGB eta and kappa values are, somehow, derived from the spectral ones, and then plugged into the Fresnel equations to go directly to the final RGB values. This doesn't add any correctness over using a principled Fresnel approximation like the Cook-Torrance one, rather the opposite. While Cook and Torrance were definitely onto something with their Fresnel approximation, it also requires, in addition to f0, a single complex IOR value. This is much less convenient than only using f0, and may be why this approximation did not find wide use. One tweak was needed to make it a truly production-friendly solution, as shown in Schlick's 1994 paper. The explicit goal was to create a simplified version of the Cook-Torrance Fresnel approximation that would not require any IOR values, only f0. The two approximations have a similar structure, though Schlick's is indeed simpler. The resulting Fresnel term is highly expressive, able to cover both dielectrics and metals by simply changing the value of f0. It's important to note that this approximation is not simply an optimization. When it was published, it was the most correct Fresnel term for the majority of practical rendering applications, both real-time and offline. How much accuracy is lost by removing the IOR parameter? Let's compare it to the ground truth. When we flip between them, we see the error is slightly larger than the original Cook-Torrance approximation. But this is just copper. How do other substances fare? Here is the Schlick delta E2000 error, averaged over all incidence angles for a variety of materials, with metals and dielectrics each sorted in order of increasing error. The errors in metals vary quite widely. In contrast, all the dielectrics fall in between aluminum and palladium. We see that copper is a material for which Schlick performs unusually well, so let's look at some more representative materials. Aluminum and the SF11 glass are each reasonably representative of their class. In addition, we will also look at the worst-case material, which is chromium. Here are plots and color strips for aluminum, first for the Schlick approximation, then the ground truth. When we flip between them, we see that aluminum has a dip near 90 degrees that the Schlick approximation does not reproduce. Now glass, first the Schlick approximation, and the ground truth. Flipping between them shows that, as is typical for dielectrics, there isn't a dip, but rather a slight mismatch in the curve shape, around 60 degrees. And finally, the Schlick approximation for chromium, and the ground truth. When we flip between them, we see a more prominent version of the missing dip we saw earlier with aluminum. The 2005 paper by Lazányi and Zermay-Kallos attempted to improve the accuracy of the Schlick approximation for metals by adding an additional term aimed specifically at reproducing the missing dip. The approximation also added 2 additional parameters. The authors proposed setting A to 2 times eta, but then we need an IOR sample of the material. And as pointed out by Sébastien Lagarde, the value of alpha depends on the extremum of the error term, which has no analytical solution. Probably due to these difficulties, this approximation did not see significant production use. 2007 was the beginning of the first wave of significant adoption of physically motivated models in film and game production. The SIGGRAPH 2012 publication of the Disney principled shading model, first used in Wreck-It Ralph, was hugely influential and to my mind marked the end of the first wave. Note that all of these shows and games used the Schlick approximation. To be more precise, most used it as originally published, but some used a generalized form of the Schlick approximation that added 2 parameters, a 90-degree color f90 and a Fresnel power p. Why are these extra parameters good for production use, while those in, for example, the Lazányi approximation are not? They are easy for artists to control, and they have default values that revert to original Schlick. Note, these parameters were added to increase expressivity, not accuracy, but they could increase accuracy in some cases that aren't modeled well by the Fresnel equations, like loosely packed fine dust. The models we've discussed so far follow the same approach as Cook and Torrance's color interpolation approximation, which is really the correct approach for anything other than a spectral renderer using accurate eta and kappa values. That is not the case for this next approximation. In 2014, Gulbrandsen proposed a new parameterization for the Fresnel equations. Unfortunately, it is based on the approach of computing the Fresnel equations for RGB values, which we showed earlier to be unsound. In this paper, the RGB Fresnel equations were reparameterized to use f0 and the new edge tint parameter g instead of eta and kappa. Effectively, these parameters are a user interface on top of eta and kappa. Like f0, g is an RGB parameter where each channel is in the range of 0 to 1. However, fundamentally, the g edge tint parameter is unlike f0. It is far more akin to eta and kappa. The g parameter has no perceptual analog, and only an indirect and nonlinear relationship to final rendered colors or perceptual stimuli. It superficially resembles a color, but it really isn't one. This has some implications that we will cover later. Perhaps due to some misplaced perception of improved correctness, this model is seeing increasing use in film rendering. Besides FrameStore, where it originated, it is used by Weta-Digital and others, often in a dedicated conductor node next to Fresnel dielectric nodes, as an Autodesk standard surface shown here. At Sony ImageWorks, this Fresnel model is an artist selectable option alongside Generalized Schlick. This growing use of a fundamentally unsound model was my primary motivation for working on this talk. Last year I presented a model that attempted to include the metallic dip, but without the shortcomings of other models that do so. It was a reparameterized version of the Lazányi approximation. The alpha parameter was fixed at a value of 6, and a new parameter, f82, was introduced, from which the value of the other Lazányi parameter, a, is calculated. Like f0, f82 is defined as the reflected color at a particular angle. Although this approximation does overcome many of the shortcomings of the g edge tint model, it still requires another parameter in addition to f0. It is unclear whether the additional expressiveness and potential for increased accuracy is worth this cost. One limitation of the model is that certain extreme combinations of f0 and f82 values can cause the resulting curves to go below 0 or above 1, in which case they need to be clamped, causing C1 discontinuities. Bending the concept of a history lesson by extending it 15 minutes into the future, I'll briefly mention the very next talk in this course, which will be presented by Laurent Bilcourt. This work extends the interpolation approach of Cook, Torrance, Schlick, and Lazányi to interpolating entire curves. It preserves the fundamental soundness of the interpolation approach while opening up new classes of Fresnel models. Which brings us to here and now. I will next discuss some common misconceptions about the Schlick model. Perhaps the biggest is that there is an accuracy problem with Schlick that needs to be solved. The type of plots I showed earlier can be misleading. Metal Fresnel curves typically have a region where the reflectance is pretty much constant, a region where the curve changes slowly, and finally a region where the interesting edge behavior, like dips, tends to occur. But foreshortening tends to flatten the edge regions, making them cover fewer pixels on screen, so this edge behavior is less prominent than it would seem from the plots and color strips. You may recall that these three materials ranged from medium to high error for the Schlick approximation. Let's compare renders using round tooth curves with renders using Schlick. Flipping between them shows differences that are less blatant than we would expect from looking at the plots, but I would argue that even flipping isn't the most relevant test. Flipping between images is useful to zero in on small differences when authoring a look. But if we are worried that a model isn't accurate enough, it's worth asking if we can even tell the difference when looking at them side by side. Can you honestly say that one of these looks more realistic than the other? Remember that Chromium was the material with the worst error for Schlick. If you are wondering, the ground truth image is the one on the left. Here's a similar comparison for glass. Differences that were noticeable when flipping back and forth are hard to see side by side. Definitely neither one is clearly more accurate. By the way, here the ground truth image is the one on the right. Such errors might be worrisome for predictive rendering applications, but not for movies or games. Most of us do entertainment rendering, not predictive simulations. Yes, photorealism is important, but it's easy to become overly enamored with the data on, for example, refractiveindex.info. I'm as guilty of this as anyone. Remember that the measured data is for 100% clean and pure laboratory-grade materials, in contrast to production CGI materials, which are messy, dirty, oxidized, and heavily artistically tweaked. Obsessing over a few percent closer match to curves calculated from such data is counterproductive. Heck, even when we need to match on-set materials precisely, those materials are often not what they would seem. The L337 droid in Solo, a Star Wars story, was played by an actress in a practical costume, which the CG render needed to closely match. But when the reference material swatches for L3's costume were scanned by Wenzel Jacob for the EPFL material database, the results were surprising. These reflectance spectra are from the metallic material swatch, which in the film appears to be an ordinary unpainted metal, perhaps steel. But these wiggles aren't like any metal that ever existed. It turns out that the metallic areas of the costume were actually multiple thin layers of metallic paint, producing an interference effect, which in turn produced these anomalous wiggles. We must remember that the goal of production rendering is first and foremost artistic expression, to which physical accuracy must always be subservient. For example, it would be valid to complain that Schlick isn't expressive enough for artists who need to control edge color. And then we could discuss if generalized Schlick F90 or reparameterized Lazányi F82 or the G edge tint are the best way to address that. But that's a very different conversation than worrying about the missing dip in measured metals. Another misconception is that Schlick can't handle transparent materials, specifically internal reflection. Internal reflection is when light reflects from the inside of an object surface. The Fresnel equations are symmetrical, with the same result if incoming and transmission vectors are swapped. And Snell's law tells us that here the transmission angle is greater than the incidence angle. This implies that the Fresnel curve for internal reflection will resemble a squeezed version of the curve for external reflection, with the same value for f0. We see that the internal reflection Fresnel plot for glass SF11 on the right indeed resembles a squeezed version of the external reflection plot on the left. This suggests that the Schlick approximation can be applied to internal reflection by simply using the transmission angle instead of the incidence angle. When computing the refraction vector, this angle is easily available. Otherwise, it can be computed from eta, which can itself be inferred from f0. Let's compare a transparent glass render using the Fresnel equations for internal and external reflection with one using Schlick for both. When we flip between them, we see the difference is rather subtle, and it is hard to see at all side by side. Neither render is more realistic than the other. Another case that Schlick is often assumed not to handle is the effect of external media. Effective IOR, and thus the Fresnel curve, changes when a material is immersed in a medium like water. This case is also important for layered materials. When using the Fresnel equations, adjusting for external media is simply a matter of dividing eta and kappa by the eta of the external medium. It's not obvious how to perform this adjustment with a model like Schlick that has no concept of eta and kappa, so it is often assumed to be impossible. The adjustment is actually quite straightforward for dielectrics. Here f0 is the original reflectance, f0e is the reflectance of the external medium, and f0' is the adjusted reflectance. Once f0 is adjusted, the overall Schlick curve compares reasonably well to the ground truth. Often the IOR of the external medium is specified instead of its reflectance, but it's easy to compute one from the other, and you even save a square root. But what about metals? The external media adjustment depends on both eta and kappa, so it cannot be inferred just from f0. It turns out that just applying the dielectric adjustment to metals gives pretty good results, especially for low IOR external media, which are the most common case. With high IOR media, like diamond, then some metals do get overly dark colors. If you need accurate renders for metals embedded in diamond, then accuracy for the high IOR case can be improved by tweaking the formula slightly, at the cost of making it asymmetrical. Switching internal and external IR no longer gives the same result. Here are the results for the tweaked formula. Now, let's turn to discussing the G edge tint parameter, introduced in the paper Artist-Friendly Metallic Fresnel. Each parameter that an artist needs to paint is an added burden, so there should be a commensurate benefit. If the parameter can be left at a default value, like the generalized Schlick F90 parameter, for example, then it's harmless. But as we shall see, this isn't the case for G. Furthermore, despite the title of the paper, G is actually not artist-friendly. Really not at all. Let's discuss why. First, let's define what makes a parameter artist-friendly. Parameter values must have an intuitive relationship to surface appearance. For a color parameter, that color should be visible on the surface. Diffuse albedo and F0 are good examples of this. Unlike F0, the edge tint G is not guaranteed to be equal to the reflected color at any angle. I will demonstrate this with some color strips for a few metals. Each metal has 3 stacked strips. The middle one shows the ground truth Fresnel color from 0 degrees on the left side to 90 degrees on the right. The top and bottom strips each have a solid color, F0 and G respectively. Note that the top and middle strips match closely over the left half of the strips, which shows why F0 is a good parameter for painting. These strips tend to have a lot of variation close to 90 degrees, so I'll add a second figure zooming in on the last 10 degrees of the range, with the top strip removed since F0 isn't relevant for these angles. These strips are for chromium. We see that the G strip on the bottom doesn't match the Fresnel color, the middle strip, at any angle. It has a colder hue. This one is for gold. We see that G has a lemony hue, which doesn't resemble the actual reflected color of gold at any angle. And finally, iron. Again, the hue and saturation of G is different than the actual reflected colors. From these examples, it is clear that the relationship between the value of G and surface appearance is not at all intuitive. The visual effect of changing a parameter by a certain amount should be roughly constant over the parameter range. A good example is GGX roughness, with a commonly used remapping first suggested by Brent Burley. This is not the case for G. These renders increase G in equal-sized steps across the 0 to 1 range. It's hard to see the difference between consecutive values for side-by-side images. So we'll show some pairwise flip comparisons. Here's a render with G set to 0. And here is G set to 0.1. Flipping between them shows literally no perceptible change. Now let's look at a pair closer to the middle of the range. Here is a render with G set to 0.5 and 0.6. When we flip between this pair of images, there is a very, very subtle difference. You can see a bit of darkening on the lower left edge of the sphere if you look closely. Now let's look at a pair at the top of the range. Here is a render with G set to 0.9 and to 1.0. Here the difference is quite noticeable. With an artist-friendly parameter, each of these pairs would have about the same visible difference. As an alternative visualization, here are color-mapped perceptual difference images for each consecutive pair of renders. This matches the pairwise comparisons we've seen. Ideally, parameters should be decoupled so that the visual effect of changing one does not depend on the value of another. For example, the visual impact of the F82 parameter shown earlier is about the same regardless of whether the value of F0 is high or low. This is not the case for G. When the value of F0 is high, G barely has an effect. Its visual impact is much stronger when F0 is low. A few primary parameters need to be set for every material. Diffuse color and specular color, or base color and metalness, are good examples. Specular roughness is another. In contrast, anisotropy and sheen are secondary parameters. It's clear that G is a secondary parameter, so it needs to have a default value that will yield a reasonable default appearance. But such a default doesn't exist for G. I sometimes hear that setting G to 0 should yield reasonable default behavior. The thinking is that this is equivalent to setting kappa to 0, which implies a dielectric, and dielectrics have pretty reasonable visual behavior. But setting G to 0 doesn't get you something that looks like a dielectric. It results in an odd darkening and discoloration at the edge. Let's compare with the ground truth curves. When we flip between them, the dark discolored edge is pretty noticeable, and it's even visible when we look at the renders side by side. Here's a closer look. You can see a bluish rim in the G equals 0 render. The reason is that the combination of high reflectivity and 0 kappa implies an overly high value for eta, much higher than any dielectric or even metal. This causes an exaggerated dip, which is sharper for channels that are higher at 0 degrees, causing a color shift. Well, how about setting G to 1? That's the default that Autodesk Standard Surface uses. Setting G to 1 results in a washed out, desaturated appearance around the rim. Again, let's compare it to ground truth. Flipping between them shows a washed out effect that extends quite a bit inwards from the edge, and is visible even in side-by-side renders. Again, looking at the curves can shed some light on what is going on. We see that they start going to wide at around 30 degrees, which is a much smaller angle than usual. This causes the surface to appear overly desaturated. Maybe some other default value? I don't know. I've tried using mid-gray and a bunch of other values. Each option I tried looked wrong for some metals. This is a difficult situation for a surface painter. They can't ignore the edge tint parameter, and they need to spare a fair amount of effort to find a value that leads to a reasonable look. In conclusion, we can see that G doesn't fulfill any of the requirements for an artist-friendly parameter. Earlier I mentioned that performing nonlinear operations on RGB quantities can cause problems. I'll now elaborate on this a bit. Parameter value blending is an extremely common operation. It happens as part of texture filtering and when combining different materials when authoring. Ideally, blending the Fresnel parameters of two materials would give the same result as evaluating Fresnel for each material separately and blending the result. That is the case for the Schlick model since it is linear, but not for the G edge tint model. This table shows the errors introduced by blending F0 and G values for different pairs of metals. To be fair, these errors aren't large, around 1.5 times to 2 times the just noticeable difference. But material authoring often involves multiple chained blends, so it is disconcerting to have errors introduced at each step, even if small. In production rendering, we sometimes need to convert parameters between color gamuts. To preserve the material appearance, shading with the converted parameters should give the same colors as shading in the original color space and then converting the result. This is again true for the Schlick model due to its linear nature, but not for G edge tint. Overall, these errors are smaller than the blending case. Some of the more strongly colored metals have errors of about 1.5 times the just noticeable difference, which isn't that bad. Still, with a linear model like Schlick's, these errors don't exist at all. Color space conversion is a lossless operation, as it should be. Finally, using the Fresnel equations in your shading model is just plain expensive. Instead of something nice and cheap like Schlick, you get a wall of math for Fresnel's equations themselves, with a few extra bricks for converting the edge tint parameterization to eta and kappa. This math is commonly used in dedicated conductor lobe, so we also need to calculate the dielectric version of the equations and mix the results. It would be one thing to spend all this extra computation if there were a significant benefit, but I hope I have shown that the benefit is dubious, perhaps even negative. To conclude, the switch away from Schlick's approximation to models based on direct use of Fresnel's equations was unfortunate. For many applications, the Schlick model, either in its original or generalized form, is in the sweet spot of expressivity, cost, and simplicity. When the Schlick model isn't enough, it's worth exploring alternatives such as Reparameterized Lazányi, or the models presented in the next talk. Or come up with your own model. If you find a good one, please let the rest of the industry know about it. And finally, I'd like to acknowledge some of the people who helped me on this project, and thank you for listening.